Alright, this is just a quick lesson on free fall from the freely falling bodies section of the physics book. Free fall is something we'll deal with frequently throughout the next few chapters, or this chapter at least, and all that means is if let's say you've got some person here standing at the edge of a cliff or something here, and they have some ball and they just let go of the ball. They don't throw it down, they don't throw it up, they don't throw it anywhere, they just let go of it. And then the ball is going to move due to the acceleration of gravity. So it's going to just fall at 9.81 is usually what we use, meters per second squared. And since it's free falling, we denote this as a negative value, since if we were working in such of an XY coordinate system, where the origin, where he dropped it, would be at the origin, and so it would be going in the negative X direction. And so that's why it's negative. But your end result is probably going to be a magnitude, which would be a positive answer. You want to be really careful about how you choose, how and when you choose this to be negative, and when you choose it to be positive. So I'll be working about 5 to 10 problems here, explaining all that. So we'll get into detail. But free fall is just dropping something. So example, free fall. I dropped it. And in free fall, anything you drop, if you neglect air resistance, will drop at the same speed, because we have a constant of gravity, which is negative 9.81 meters per second. So if I dropped this piece of paper and this pen at the same time, if there wasn't any air, they would hit the ground at the same exact time. But the air holds this up because it's spread out. I'm sure we all remember learning that from elementary school. But that is what free fall is.
Projectile Motion Series, M&M Quiz 2148. Welcome. Before we get to the problem, we have a velocity vector of magnitude 24 meters per second, and the angle is 30 degrees with respect to the horizontal. Assume positive x is defined as to the right, and positive y is defined as vertically up. No air resistance. Assume no air resistance. So we have a projectile that is kicked at an angle of 30 degrees with respect to the horizontal. What is the velocity vector? What is the magnitude of the velocity vector? 24 meters per second. For those of you who know trig, you can go ahead, get the horizontal and vertical components at the start. So a ball is kicked as shown before at 24 meters per second. And what is the angle? 30 degrees. The initial velocity vector makes an angle of 30 degrees with respect to the horizontal. Horizontal component then becomes 20.78 meters per second. Vertical component then becomes 12 meters per second. So here is the question. Which component is going to change as a function of time? Is it the horizontal component? Or is it the vertical component? Is it A or is it B? Welcome to hecanhelp.com. Welcome, 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 welcome. You know that the Earth is going to pull on the object along the vertical. This causes the vertical velocity vector to change as a function of time. Because the Earth is pulling on the object along the vertical, only the vertical component of the velocity vector is going to be affected. The horizontal component is unaffected by acceleration due to gravity, which is completely along the vertical. So your 24 meters per second at an angle of 30 degrees is equivalent to 20.78 along horizontal and 12 meters per second along the vertical. 20.78 along the horizontal and 12 meters per second along the vertical. Please don't forget the vertical component at the very beginning, it is positive, right? So if you kick something like that, it is going to go like this and reach the maximum point. So this is A, this is B, and from point B, the vertical component of the velocity vector is negative because it's on its way down. So beyond B, it is on its way down. So this is point A. At point A, the vertical component is positive. At point B, it is 0. And beyond point B, the vertical component is negative. What about the horizontal component? The horizontal component is unaffected by gravity. So it remains exactly the same as before. So whatever it had at the start, it'll keep that forever throughout the trajectory. So what is our answer? The answer is B.
Okay, how are vectors different from scalar quantities? Well, let's talk about vectors again. Vectors have a magnitude and a direction. So examples that we talk about as vectors are things like velocity, meters per second east, or acceleration, 9.8 meters per second squared, in the 180-degree direction. Okay. So vectors have a magnitude and a direction. Scalar quantities are things that just have a magnitude or an amount. So something like a mass in kilograms, or a volume in liters, or other quantities like that, densities and so forth. So these are units that don't have a direction, but they do have a magnitude or an amount. And that's the difference between a vector and a scalar quantity.
In their state of motion unless acted on by an outside force. This means that moving objects will stay moving and still objects will stay still unless you push or pull on them. There are two safety devices in your car to protect you from the effects of inertia. The first is your seat belt. When the front end of your car rams another object, your car will suddenly stop or slow down. Because of inertia, your body will want to stay moving at whatever speed it was moving before the accident. If you're not wearing a seatbelt, this means you will hit a windshield. The seatbelt provides a force to stop your body's forward motion. The second safety device in your car is a headrest. When your car is hit from behind, the car is suddenly pushed forward. Your head will want to stay still, but your body will be pushed forward by the seat. This causes your head to feel like it is snapping back. Your head is actually staying still because of inertia, while the rest of your body is being pushed. Your headrest pushes your head forward with your body so that you don't suffer from whiplash. Look at the difference between a headrest that is properly set versus one that is set too low to push your still head forward.
And here's the first of a set of examples on Newton's second law of motion. Here we have an object with mass m. Let's say that the mass is equal to 3 kilograms, and it's going around a circular path of radius 5 meters with a velocity, a tangential velocity of 2 meters per second. And what is the force required to keep it in that circular motion? Remember, Newton's first law says that if there's no force acting on the object will simply go in a straight line path at a constant speed forever. And since it's not doing that, it's going in a circular path, there must be some force acting on it. So what is that force? Well, it's known as the centripetal force, the force required to keep it going in a circular path, because it requires centripetal acceleration to do that. And the equation for centripetal acceleration is v squared over r, as we had seen in an earlier video. So the centripetal force required is equal to what? Well, let's go to Newton's second law that says that F equals ma. And so since here we're dealing with centripetal force and centripetal acceleration, we can write that F sub c, centripetal force, is equal to m times a sub c, centripetal acceleration. And since that's equal to v squared over r, we can say that F sub c is equal to m times v squared over r. So all we have to do now is plug in the mass, the radius, and the velocity, and we find out what the force is. So in this case, we have a mass of 3 kilograms, a velocity of 2 meters per second. We have to square that, and we divide that by the radius of 5 meters. So 2 squared is 4, 4 times 3 is 12, divided by 5 is 2.4, so it would be 2.4 newtons. And that would be the force required to keep the object going around in a circular path. So that's pretty straightforward. Again, the definition here is F equals ma, and it doesn't matter what the F or the A is. If it's centripetal, we use the very same equation, and then the equivalent for the centripetal acceleration to fill out the equation F equals ma, known as Newton's second law. And that's how you do that.
Hi, my name is Subha Agarwal and I'm a math expert. And today we're going to go over accuracy versus precision in measurement. So accuracy is how close a value is to the actual value. And precision is how close the values are to each other. So to give you a quick visualization of what that might look like. Say we have a dartboard, right? And we have 3 little things in here. Now if someone is very accurate, that means that they're getting the darts really close to the actual value, or that bullseye. However, if somebody is very precise, it could just mean that they're getting a bunch of darts really close to each other and nowhere near that bullseye. And that's accuracy and precision. My name is Subha Agarwal, and thank you for taking an interest in math.
Hi, my name is Keela Mazzone, and I'm a physics teacher on Long Island. Today I'm going to talk to you about Newton's second law. Newton's second law says that a net force causes a mass to accelerate. So in order to understand it, we need to first know what a net force is. So in order to demonstrate that, I have my guest, Eric Mazzone. A net force is a force that is unbalanced. Here's an example of a balanced force. I'm going to apply a force to this foam ball. His hand is going to apply a force opposite my force in order to balance it out. So when I hit the foam ball, the ball doesn't go anywhere. And that would be a balanced force. Thank you, Eric. A net force, or an unbalanced force, is one that does not have a force opposing it. So now when I apply a force, the ball accelerates. That's a net force. Now that we know what a net force is, we can see how a net force affects 2 different masses. My first mass is this foam ball. I'm going to apply a net force that's going to cause this mass to accelerate. The mass accelerates. Now, let's see how that same net force causes a second mass to accelerate. So here, I have a bowling ball. Same net force. Not quite the same acceleration. Newton's law, a net force causes a mass to accelerate. The larger the mass, the less acceleration if you have the same net force. In order to give the bowling ball the same acceleration as the foam ball, I'd have to apply a lot more force. But unfortunately, that's not going to happen. Thanks for tuning in today and learning about Newton's second law.
Good morning, Martin.
Nigel, you look sad. What is wrong?
I'm worried about the science test today.
Have you been sleeping in class again?
Yes.
If you would lose some mass, you might have more energy and be able to stay awake in class.
I do not see how losing mass can help me. I should lose some weight.
No. Mass is the amount of matter in an object. If you lose mass, there will be less of you.
But that is losing weight.
No. Weight is how much gravity is pulling on you. If you just want to lose weight, then go to the moon.
What does going to the moon have to do with losing weight?
Nigel, the moon has less gravity.
This is getting complicated.
The moon has about 1/6 of the Earth's gravity. So if you weigh 60 pounds on Earth, you will weigh 10 pounds on the moon.
Then I would have more energy and could stay awake in class.
No.
But you said I would weigh less.
You would weigh less, but all of your mass would still be there.
All of my mass? I still do not know what you mean by my mass.
Your fat. Your mass is all of your fat.
You do not need to be rude.
Sorry. Let me try this again. Less fat is less mass. Less mass is less of you. So the gravity will be pulling on you less. This will make you weigh less.
I think I understand. If I have less fat, then I will have less mass. If I have less mass, then the gravity will pull on me less. And that will make me weigh less. Do you want to get a cheeseburger and fries before the test?
Yes. Then we can discuss Newton's first law and how mass is a measure of inertia.